This section discusses hypothesis test for one population mean when population standard deviation sigma is unknown. In practice, the population standard deviation sigma is usually unknown. How to perform a hypothesis test for one population mean with unknown sigma? Recall what we did when discussing confidence intervals for mean with unknown sigma. It is very similar. First, we replace sigma by the sample standard deviation S when computing the test statistic. Next, make sure to replace the standard normal distribution by t-distribution with n-1 degrees of freedom. The resulting procedure is called the one-mean t-test or simply t-test. The test statistic is t equals x bar minus mu0 divided by sigma over square root n. Before we move on, we need to discuss how to calculate p-values for a t-distribution, or how to calculate probabilities for a t-distribution. We can definitely use Excel. The name of the function is t.dist. It has three arguments. The first argument is the t-value. The second argument is the degrees of freedom. And the third argument is always true. The slide lists how to calculate p-values for these three scenarios. For a two-tailed test, the p-value is 2 times the probability to the left of the negative absolute value of t0. Pay attention to the absolute function. Do not miss it. For a one-tailed test, to calculate the p-value, we directly use t0 as the first argument. Occasionally, we can also use a t-table to estimate p-values. Notice that because a t-table only contains a few values, we cannot get an accurate p-value. We can only know the range of p-values. Because we only need to compare p-value with significance level alpha, a rough range of p-value is enough for us to draw a conclusion about the hypothesis test. Let's check some examples. Estimate the p-value for a left-tailed test with n equals 12 and t equals negative 1.938. Because it is a left-tailed test, the p-value is the probability to the left of negative 1.938. However, a t-table only lists probabilities to the right of a value. By symmetry, the p-value is equal to the probability to the right of positive 1.938. Because n equals 12, the number of degrees of freedom is n-1 equals 11. If we use the t-table in the textbook, in the row corresponding to degrees of freedom equals 11, the value 1.938 is between 1.796, which is t.05, and 2.201, which is t.025. Therefore, we know that the p-value is somewhere between 0.025 and 0.05. If the significance level is 0.05, we reject H0. If the significance level is 0.01, we do not reject H0. In the second example, estimate the p-value for a two-tailed test with n equals 25 and t equals negative 0.895. For a two-tailed test, the p-value is the probability of two parts as shown in the graph. We can find the probability for one of them and then multiply it by 2. Because n equals 25, degrees of freedom is n-1 equals 24. Because the t-value 0.895 is smaller than 1.318, which is t.1. We know that the probability to the right of 0.895 is larger than 0.1. Therefore, the p-value is larger than 0.2. If the significance level is 0.05, we do not reject H0. Let's summarize how to conduct a one-mean t-test. The assumptions include simple random sample, normal population, and the population standard deviation sigma is unknown. If the sample size is large, we can weaken the normality assumption. What discussions on the one-mean z-test, such as sample size and outliers, are also applicable to one-mean t-test. To perform a one-mean t-test, we first need to correctly identify the null and alternative hypothesis. The null hypothesis is always mu equals mu0, where mu0 is a given constant in the problem. There are three different alternative hypotheses. Which one to use in practice depends on your research questions and your understanding about the applications. Then we need to decide on the significance level alpha. This choice of alpha is by convention. The most common value is 0.05. Occasionally, we may use 0.01 or 0.1. Compute the test statistic as x bar minus mu0 over s divided by square root n. Here, x bar is the sample mean, s is the sample standard deviation, and n is the sample size. Note that no matter which alternative hypothesis you use, the test statistic is always the same. We can draw a conclusion based on the critical value approach or p-value approach. For the critical value approach, we find critical values according to different alternative hypotheses. Notice that the number of degrees of freedom is n-1, while n is the sample size. We need to use a t-table or Excel to find these critical values. For two-tailed test, the critical value are plus minus t alpha over 2. The rejection region contains two parts, less than negative t alpha over 2 and larger than t alpha over 2. For left-tailed test, the critical value is negative t alpha, and the rejection region is less than negative t alpha. For right-tailed test, the critical value is t alpha, and the rejection region is larger than t alpha. If the test statistic falls within the rejection region, reject H0. Otherwise, do not reject H0. We can also draw a conclusion to the hypothesis test using the p-value approach. For two-tailed test, the p-value is the sum of two parts, probability less than the negative absolute value of t0 and the probability larger than the absolute value of t0. Because of symmetry, we can calculate one of the probability and then multiply it by 2. For left-tailed test, the p-value is the probability less than t0. For a right-tailed test, the p-value is the probability larger than t0. After calculating the p-value, we compare it with the significance level alpha. If the p-value is less than or equal to alpha, reject H0. Otherwise, do not reject H0. Last, make sure to interpret the result of the hypothesis test. Notice that the hypothesis test is exactly for a normal population and is approximately correct for larger samples for non-normal population. It is guaranteed by the central limit theorem. Let's check one example. A lake is classified as non-acidic if it has a pH greater than 6. Researchers measured pH levels for samples from 15 high mountain lakes in Southern Alps. At the 5% significance level, do the data provide sufficient evidence to conclude that on average, high mountain lakes in the South Alps are non-acidic? In this problem, we want to compare the mean pH level with 6. We do not know the population standard deviation and need to use one mean t-test. The sample size is 15, which is small. We need to check the normality assumption. The one mean t-test is applicable for small sample size only when the population's distribution is very close to normal. The normal probability plot is displayed in the slide. All points roughly fall on a straight line, which indicates that the normality assumption is appropriate. The null-hypothesis is mu equals 6. The alternative hypothesis is right-tailed. We want to know whether the lakes are non-acidic, and non-acidic means pH level larger than 6. Hence, we choose the right-tailed alternative hypothesis. The significance level is 0.05. We can calculate the test statistic as follows. Notice that x bar is the sample mean, s is the sample standard deviation, and n is the sample size. Do the math and we get t0 as 3.458. The sample size is 15, and the number of degrees of freedom is n-1 equals 14. We can draw a conclusion using either the critical value approach or p-value approach. Using the critical value approach, the critical value is t.05, which is 1.761. We can find this number using a t-table. Make sure to check the row corresponding to 14 degrees of freedom. The test statistic t0 equals 3.458, which is larger than the critical value. It falls within the rejection region. Here, we reject H0. We can also use the p-value approach. Use Excel to calculate the p-value. It is 0.00192. The p-value is smaller than the significance level, 0.05. We reject H0. Both approaches lead to the rejection of H0. At the 5% significance level, the data provide sufficient evidence to conclude that on average, high mountain lakes in the southern Alps are non-acidic.